Dear students, now we are going to our new chapter, that is spectrum of compact operator. So we know what is spectrum of an operator. X be a normed space and A is an operator, that is A is from X to X. Then the spectrum of A is denoted as sigma A and is defined as set of all k following k such that A minus ki is not invertible. And we know what is this compact operator. So A is in CLXY or A is in CLX. That's a compact operator. So A is compact means then A is a compact linear operator means A of xn. For every bounded sequence xn in X, A of xn has a convergent subsequence. Okay. So we know what is the spectrum and the compactness. So in this chapter, let us discuss about the spectrum of such a compact operators. So for that, first we are going to a lemma. That's an interesting result. So the lemma states that let X be a normed space. X be a normed space. A is in CLX. A is a compact linear operator on X. A is in CLX. And there exists some non-zero k following k if sequence xn is a bounded sequence. Bounded sequence means there exists some alpha positive such that norm extends to be less than alpha for n equals 1, 2, 3, etc. In X, xn be a bounded sequence in X such that axn minus kxn goes to some y following X. Axn minus kxn tends to y, goes to y in X. Then there exists a subsequence xnj of xn such that xnj goes to x in X, then ax minus kx equals y. Ax minus kx equals y. Then there exists a subsequence xnj of xn such that xnj converges to x in X and ax minus kx equals y. So how to prove this lemma? Here X is a normed space and A is a compact linear operator. So A is a compact linear operator and what is xn? Xn is a bounded sequence in X. So we know that by a non-result, if A is a compact linear or F is a compact linear map from X to Y, then for any bounded sequence xn in X, f of xn has a convergent subsequence in Y. Here since A is a compact linear operator and xn is a bounded sequence in X, then there exists a subsequence. Then by using the theorem, there exists a subsequence xnj of xn such that axnj, the sequence axn has a convergent subsequence. The sequence axn has a convergent subsequence in X. That means there exists a subsequence xnj of xn such that axnj converges to some y in X. Okay, or axnj converges to, converges to some y here. So axnj converges to some z in X. Because axn has a convergent subsequence. So for any subsequence xnj of xn, axnj converges to some z in X. Okay. Now, what about kxnj? For any non-zero k, we choose k is a non-zero element. So consider this kxnj. Kxnj equals this kxnj minus axnj plus axnj. Okay, right. So this should be converged to kxn minus axn minus kxn goes to y. So axn, kxn minus kxnj, since xnj be a subsequence of xn, surely axnj minus kxnj converges to y. Therefore, kxnj minus axnj converges to some minus y. Why? Because of this argument. Okay, minus y plus and axnj converges to z. So clearly, this kx and j converges to where? Kx and j converges to z minus y. Means x and j converges to where? Z minus y by k. That should be fallen x itself. Clear? Now, therefore, it is enough to show ax minus kx equals y. So, but a is continuous. What is a? A is in CLX. Means a is a compact linear operator. A is compact. Means a is bounded and totally bounded and complete. Therefore, the continuity of A is preserved. Since A is continuous, what about Ax minus Kx? We have Ax minus Kx equals, because of the continuity of E, Ax minus Kx equals limit j goes to infinity. A x and j minus Kx and j. Ax and j minus Kx and j. Okay. Limit Ax and j minus Kx and j. That equals limit j goes to infinity ax and j. What is ax and j? That goes to z minus limit j goes to infinity kx and j. That is minus y plus z. So it is nothing but y. This y is in where? Y is in x. So clearly ax minus kx equals y. That is what we require. So this is our level. Agree.